Hi all, in this video we are going to see the non-recursive descent parser, which is also known as LL1 parser in compiler design. As you are aware, parsing is the second phase of the compiler design, which is also known as syntax analysis, where the parser checks the grammatical structure of the source code against the context-free grammar. It also generates the parse tree, which represents the hierarchical structure of the program. The following are the working of the parser or the functionalities of the parser. The parser will do the structural validation against the syntax rule of the programming language with the grammatical thing which is available in the context-free grammar. And it also creates the intermediate representation, which is the parse tree, and it also do the error detection and reporting. Finally, it will implement the error recovery in the panic mode to recover from the errors so that the compilation process can continue without any interruption. This is the workflow of the parsing during the compilation. The first phase of the compiler design is a lexical analyzer, which will convert the source code into tokens in terms of the regular expression. And now the second phase is the parser, which gets the input as a token from the lexical analyzer, and it will create the parse tree. And while doing the parsing, it will check the tokens syntax by using the grammar, which is available in the context-free grammar. And it also produces the parser tree and then error recovery, error detection, and also error recovery. And the output of the parser will be going as an input of the next stage, which is called as the intermediate code generation of the compiler phase. And what is meant by context-free grammar? Context-free grammar is a combination of non-terminal and it having the terminal, and the next one represent the production, and the last one is the start symbol. So if you see here in the left side, we have the non-terminals. Non-terminals, which are the non-terminals from the production, which can be an expression, term, or a factor. And then we have the terminals. And next is the production rules. And finally, we have the start symbol of the particular production. And the parser will be basically divided into two types. One is the top-down parser and the next one is the bottom-up parser. So in top-down parser, the parser starts from the root node, that is from the start symbol, and it will move towards the leaf, that is the tokens. How it is doing the job? It will do the job of expanding the non-terminals to reach the tokens. And it uses the leftmost derivation for doing this particular process. There are various types of top-down parsing. Mainly, we have two types of top-down parsing. We have the recursive descent parsing and the non-recursive descent parsing. And next one is the bottom-up parsing, which will start from the input tokens, that is from the leaf. It will move upward to the root or the start symbol. By doing the job of applying the reduction rule, it will reach the root node. And it uses the rightmost derivation in the reverse order. And the examples are shift reduce and the LR parsers. And now we are going to use with the predictive parser, which is nothing but a type of a top-down parser. It is also known as non-recursive descent parser or LL1 parser, or the parser without backtracking, or it can be a dynamic parser. It uses the parsing table to generate the parse tree instead of backtracking procedure. And the parser will have the parse table, and the input it will parse with the help of the stack, and we get the output. So now when you use with the LL parser, you have to understand the grammar will not be ambiguous, it will not have left recursion, and it will not be left factoring. So first we have to know what is meant by ambiguous. A grammar can be ambiguous if it produces more than one parse tree for the same input string. If you see here, this is our input string, and this is one parse tree which produce the string, and also this is another parse tree which also produce the same input string. So the grammar can be ambiguous if it has more than one leftmost derivation. So you take this production. So from the leftmost derivation, the E will be first replaced with ID. Then in the next step, the E will be from the leftmost, the E will be replaced with E star E. The next step, it will be derived to ID star E, and finally it will reach to ID plus ID star ID. Same thing, here I have the production E star E, which is also starting with the leftmost derivation. So here this E will be replaced with E plus E star E. Then from the leftmost, E will be derived to ID. Then the next E will be derived to ID. And finally, in the last step, so we are getting the input. So if your grammar has more than one leftmost derivation, or if the input string produces by more than one parse tree, then the grammar is ambiguous. So here this grammar is an ambiguous grammar. And what is meant by left recursion? So left recursion will happen when the non-terminal symbol derives itself. That is, the left hand side non-terminal and the right hand side the first non-terminal. So both the things having the same non-terminal symbol. And the left factoring occurs when two production starts with the same prefix, then it is called as left factoring. And to work with predictive parser, first the grammar should be unambiguous, no left recursion and no left factor. And this predictive parsing basically uses the stack and the parsing table to parse the input and generate the parse tree. And here LL1 represent, the first L represent, we are doing the input scanning from left to right, or the parsing will done from left to right. And the next L represent the grammar uses the leftmost derivation. And the 1 represent one symbol at a time it will process. So that is the definition of the LL1 parser. Now moving to the algorithm to construct the LL1 parsing table. First, we have to check whether our grammar is unambiguous, no left recursion and no left factoring. After that, we have to calculate first and follow for all the non-terminals. Then you have to construct the parse tree. So now we will take one example, and this is our grammar. For this grammar, we are going to follow the things to create a parse table. And when you see this grammar, the grammar's left side non-terminal and the right side non-terminal, both the things having the same non-terminal symbol. So this is the left recursion and this is the solution for the left recursion. So we have to remove the left recursion from this particular production. So while doing so, we have the S tends to S A A. So here this represents A, this represents A, and this is alpha, and this is nothing but beta. So you apply, you convert based on this. So we are getting S tends to A, S dash, then S dash represents A, S dash empty. So similarly, the next production, A tends to A, B, C, A, D, E. So here we have to replace A tends to C, A, D, A dash, E, A dash. So A dash is nothing but B, A dash, empty string. So we'll take one example. A tends to A, B, bar, A, C, bar C. So two production having the same starting symbol. So it get replaced with A tends to A dash, C, and A dash represents B bar C. So now we have to do the first and follow. So this is our left recursion removed grammar. For this, now we have to find the first of non-terminals. So first terminal is yes. So we have to take first of S. So first of S is the first symbol A. So we have to calculate the first of A. So here, if the right HS starts with the terminal, now the right HS starts with the non-terminal. So if the right H starts with the non-terminal, copy the first of B. So first of B is here first of A. So first of A still we didn't calculate. So we have to calculate the first of A. So we take the production of first of A. The first is the terminal. So you see here the RHS starts with the terminal. Copy it to the first. Just copy the symbols into A. So the first symbol is C. The next symbol is E. So first of S is also same thing as C and E. Then followed by we have to calculate what is mean by first of S dash. So when you go with S dash, the first symbol of this particular production in the right hand side is A and empty. Next we have to go with first of A dash. So when you go with A dash, the first symbols are B and empty. So like that we have to calculate the first of all non-terminals according to the algorithm given in the right side. Now we are going to calculate the follow. So first we have to start with the follow of the start symbol. So when you have the follow for the start symbol, put the dollar symbol directly. So first I put the dollar symbol. Now I am going to check in the production in the right hand side whether any production having yes in the production rule. So there is no S. So I don't have any follow for S in the right hand side. So now I am going to use with the follow of A. So when I go with the right hand side, follow of A, I have S dash and D. So if it is a terminal, just directly put that terminal. And if there is any non-terminal following, you have to add the first of S dash. As you already know what is mean by first of S dash. So first of S dash, you having A and empty. But when you add the first of the B, you have to use only the terminals. But when you have any empty symbol, that will not be included in the follow. So instead of using that, what you have to do is you have to substitute. For example, we have the A S dash. So in this S dash, I'm just going to substitute this empty value. So my production become A. So if any symbols not following A, then I have to take the follow of the head. So follow of head is nothing but follow of yes. So A, D, union, follow of S. As I already have what is follow of S. So the symbols are A, D and dollar symbol. Now we are going to use with follow of S dash. So right hand side, the productions which are having follow. So nothing is following after S dash. So if the follow of S dash is empty, then you have to follow the head. The head of the production is yes. So I have to follow the dollar symbol. Next we having the follow of A dash. So A dash you go there. A dash production also we are having no follow after A dash. So we have to follow the head, that is nothing but follow of A. So in your production for the non-terminal, if there is no follow or we have a follow which having the empty value, then we can add the follow of A, that is follow of head left hand side to the follow of B. So that's why we have added A dash doesn't having any follow. That's why we are following the head of that particular production, that is follow of A, which containing the value A, B and dollar symbol. So as the output, we get both follow and first of the particular given production. Now we have to fill up the parse table. The parse table in the rows, we have to contain the non-terminal. So S, S dash, A and A dash. And in the columns, you have to get the terminal symbols. So A, B, C, D, E and the dollar symbol. Another one thing you have to remember, in follow, any of the follow will not contain the empty symbol. So follow will not contain any empty symbols. That's why the empty symbol we have to substitute in the production and we have to find the follow of that particular symbols. And now we are going to fill up the parse table. First, we have to take the production x tends to A S dash. So this is A tends to alpha, the production. We have to take the first of alpha. So here we have to take the first of A. So in the first of A, you have to make the entry of this particular production. So we are going with the C. We are making a entry here and also in E. So take the next production. The next production S bar, that is S bar into this empty symbol. So when there is a symbol in the first production, we have to put the entry in the first of A. First of A is always first of A, the symbol A. So we are going to put with A S dash. And now when we have a production with S tends to empty, then you have to put the entry in follow of S dash. So you can see here, when your first of alpha contains epsilon as a terminal, you have to find the follow. So follow of S dash. Follow of S dash is the dollar symbol. So we have to put the entry here. The next thing is we have to use the next production, that is A tends to C A D A dash and E A dash. So in the first production, the starting symbol, first symbol is C. So I have to put the entry in the C. So C A D A dash. In the second production, the starting symbol is E. So this production entry, we have to put it here. And the last one, A dash, which having two production, A dash B A dash and A dash empty. So here the starting symbol is B. So we are going to put the entry in B A dash. Here it is an empty. So when there is an empty, you have to calculate the first of alpha is empty, then you have to go with the follow of A dash. So follow of A dash is A, D and dollar symbol. So I have to put the entry in A and then D and then last one is dollar symbol. So whenever the production having empty, then you have to take the follow of the starting symbol. When you have the first symbol, then you can take the first of the starting symbol. Like that, you fill this parse table. So after filling the parse table, now the parsing will come into the picture. Using the parse table and the given input with the use of stack, it will parse your input string. So this is the parsing algorithm, and based on the input and the stack symbol, we are going to verify our parse table and try to accept or reject our input. So we'll see the input. The input is C, E, D, A and the N symbol. So to start with the stack starts with the dollar symbol with the initial non-terminal production, that is S. Here our input is C, E, D, A and the dollar symbol. Now we have to check in the parse table the combination of S and C. So S with the C as terminal, S is in the stack top symbol and C is the input. When you compare this thing, the corresponding production rule is S tends to A S dash. So this S now replaced with this production, but when you push it into the stack, it should be pushed in the reverse order. So S dash A. So C E D A symbol. Now we need to find the match of the non-terminal A with the input is C in the parse table. So this is the rule we have to apply. C A D A dash. Now push this in the reverse order. A dash D A C C E D A symbol. So now the top of the stack and the input both get matched. So we are going to pop the symbol C from the stack. So now we have S dash A dash D A and the input is E now. Now we have to match in the parse table A match with the symbol E. So the rule is A tends to E A dash, push it into the stack A dash D A dash E. So the top of the stack and the input is same. So we have to pop and delete the input symbol. Here pop, here delete. Now we have the inputs S dash A dash D A dash D A and the dollar symbol. So now I have a match in the parse table A dash with D. So A dash and D. So the corresponding production is empty. So we just make this is empty. Now we have the start symbol and the stack top symbol and the input symbol both are same. So we have to pop the symbol. The remaining we have S dash A dash and the symbol is S in the input. Go with A dash and A, again it is empty. So when I have an empty, it becomes S dash A here. So match with S dash and A. So we have the production is A S dash. So again we have the S dash will be now replaced with S dash A and A dollar symbol. Now the top of the stack and the input both are same. So pop A. So finally we have S dash with the dollar symbol. Go with S dash and dollar symbol. It is empty. So S dash become empty. So inside the stack also I have the dollar symbol. Input also my dollar symbol. So my input string get accepted. So this is the way how the parsing is working. So when you want to do with the parser, with the concept of LL1 parser, first we have to verify the grammar doesn't have an ambiguous and it does not have a left factor and it does not have a left recursion. After that you do with the first and follow for all the non-terminals. Based on that you can create the parse table. So once the parse table is created by using the parsing algorithm, the help of the stack and the parse table, we are trying to parse our input and to identify whether the string is accepted or not. Thank you.